Okay, I think we'll get started. So thanks everyone for joining. I'm Sam Lindsay from Antopology, and for this webinar, all of the attendees are going to be in listen-only mode. If you have any questions for the presenters, please put it in the Q&A box, and the questions will be answered at the end of the webinar. And this webinar is going to be recorded, so if any of your colleagues want to watch this afterwards or you need to rewatch it, we will be sending that out to everyone later today or first thing tomorrow. And so with that, I will pass it over to Blake Johnson from nTopology to get this started.
Hi, everyone. Thank you for joining. I'm Blake Johnson. I'm going to be starting us off. This topic here is process automation and lattice design optimization with nTopology and 3D experience. So if we could have the next slide, please. I'd just like to introduce the presenters as well as some other people that worked on this collaboration. So myself, Blake Johnson, I'm a solutions engineer at nTopology. I have a PhD in mechanical engineering from Northwestern University and a bachelor's from UT Austin. And I've been with nTopology for about a year and a half, working as a solutions engineer on the customer success team. So I work with our customers in various projects and training. We also have Glenn Larson. He's from the VIAS3D team as an application engineer. He's 12 years experience in the aerospace, automotive, and manufacturing industries and has a ASE Master Tech certification in the automotive industry, as well as Arindam Chakraborty from VIAS3D as well, the CTO there. He has a PhD in mechanical engineering and 15 years of academic and research industry and consulting experience, and has globally managed advanced engineering consulting through VIAS3D. And just an acknowledgement to some of the other people working on this project from Antopology, Daeho Hong, the product engineer, who isn't in the meeting today, but worked very hard on this, as well as Georgi Makadonov, an FEA engineer for VIAS3D, and Raghavendra Banchor from VIAS as well. So moving on, I'll talk about the agenda of this presentation. So we're going to be going through some introductory slides on the various sets of software used in this project. That includes nTopology, which I'll give, and then a variety of other software that's connected to that, as well as Process Composer, which is kind of the overall containing system. We'll give an overview of the optimization process we went with and how nTopology was used for that. Again, how other software was used in that. What the FEA analysis looks like that was performed in abaqus, and then after the topology optimization for fatigue life in Tosca and Fesafe. And we should have plenty of time for questions and Q&A section after the conclusions of that. So if we jump into it, let's start talking about nTopology. I'll just give a background on us as a company on the next slide. So we were founded in 2015. We're based in New York City. There's a lot of technology we'll get into, but the driving mission, most importantly, is that we're trying to empower engineering teams to design transformative products. Our philosophy is that the software industry has not been able to keep up with the complexity and the efficiency of computers when it comes to 3D design and manufacturing and engineering processes in general. So we're trying to develop the next generation of mechanical and 3D design software. A lot to do with that is our unique way of representing geometry. Instead of a traditional CAD representation, we use implicit modeling, which allows for extremely complex models to be developed, not only geometrically, but mathematically and in a physics-based sense. We can create structures that maybe are not creatable through pointing and clicking. And I'll show that a little more later. But yeah, the idea is we're leveraging, manufacturing methods and modern computers and trying to take 3D design software to the next level. At the same time, we're not trying to replace CAD, right? CAD has its place for designing kind of design spaces and assemblies and a lot of simulation tools, very useful with traditional CAE software. So we're here to complement and add complexity where it can't be done with traditional tools. We're used in major companies in aerospace and defense, automotive, medical, and consumer industries. And we're not going to go too deeply into kind of the use cases applications, but you can visit our website, nTopology.com, for case studies and more information like that. So if we look at the next slide, I'll talk about kind of the fundamentals of what makes nTopology different. We have these 4 categories. So the first is that the geometry created in nTopology is unbreakable. So as your complexity grows, as you have lattices or shells, things like that, what starts happening typically in a CAD program is you start getting build errors, right? It's trying to figure out where's the intersection of these 2 bodies, and when you make modifications, sometimes something will just break, some mathematical connection will break, and then downstream you'll have all these issues. So nTopology is really good about setting up a parametric design and being able to change those parameters without failure, without errors, build errors, things like that. You can really run a wide range of input parameters and always get an output, which, as we'll see, is really important in a optimization problem like we're going to look at. Another aspect of nTop is this field-driven design methodology. So a lot of important information in engineering and science can be represented as fields, right? So you can have a temperature field, right? That just means like a weather map, right? You have a domain, either 2D or 3D, and everywhere there's defined some temperature. That can be true for stress or a displacement vector, all kinds of information that we get from simulation and from experiments. And the question is, how do you take that field, not just a single value, but a field of data and directly relate that to a geometry? Like maybe take a stress and drive the lattice thickness based on where that stress is high. So this idea of spatially varying properties is a really powerful thing that also lends itself to optimization. I'll talk about that in the next slide. But what I mean to say is that, you might know that you want to have a thicker lattice where there's more stress. But the question is, how do you relate those 2 numbers, right? Totally different units, totally different kind of phenomena. So that's where optimization comes into play with field-driven design. Another thing we really focus on and push for is the idea of reusable workflows. So we can take something that an engineer might do every day for his colleague, and somebody always comes back and asks him or her to repeat this task. If we can build a little bit of intelligence and a little bit of user friendliness into that process, we can create this workflow that's reusable. So instead of having to go to this colleague of yours, you know what the inputs and the outputs are, you just share a file, and that process can be completed. So maybe it's drilling, adding holes to a feature, or running an analysis, things like that. So we really want to be able to package up the process into a black box where an input can be placed in and output can be set out. And that also has implications in optimization, right? That's what we need to set up for an optimization to work. We need to isolate what are the inputs that I care about, what's the output that I care about. And this ties into the last column here, which is knowledge, right? Capturing knowledge. Not just having a tool where you can point and click and a user always has to come in, but also creating this workflow that can, understand what the intention of the process is, give feedback, have documentation, and really be able to save time for the user, because all this communication and this intelligence built into workflow is included in the software in the file instead of attached on a Word document next to it, right? So these are kind of the four core principles of Antopology. And on the next slide, I'll just demonstrate a little bit further how that is important in the context of optimization. So I mentioned this a lot in the last slide, but with unlimited complexity, basically because of our implicit modeling techniques, we have all of a sudden so many variables to play with, right? Lattices alone, which we focus on in this talk, present many options for the user to manipulate and optimize. And so with that great level of increase in design space, it's difficult to intuit what the right designs are, and that's where optimization is key. So that's what we're going to demonstrate here. And like I mentioned about field-driven design, right? In this case, we have this field on the animated section of this on the left side. We have this field where we know we want the lattice to be thicker in that region, and thinner so I should say thicker where it's the red part of the animation, and blue can be a thinner lattice because it's less important. But the question is, what do you set your minimum and maximum thickness of this lattice, right? So there's all these kind of connections you need to make between fields and a design property, and that has a lot of open-ended implications that optimization can help with. Another key thing about nTopology and optimization is that we can control, we can set up a few inputs that are key to the design, like in this case, the lattice type, the scale, the thicknesses. We can set that up and control that externally. So we just have some inputs, produce an output, and that output can be anything from just a geometry, like a mesh, to an entire finite element analysis result, or a finite element analysis that can get sent to another piece of software. And super open-ended, right? Anything you control with a click in nTopology can also be controlled from the command line or from some interface, which you could set up manually, or in this case, we've connected that interface to Process Composer. So we're really set up well to work with an optimization protocol, and a key part of that, it's really everything I talked about in the previous slide. It's we can isolate input variables, produce all kinds of outputs. We can have a geometry that's unbreakable, so any range of inputs, you won't lose samples in your data set because of some failure. And we have this idea of field-driven design where we're looking for connections between kind of analysis results or experimental results, connecting that to a geometry. So that's all about nTopology for now. We'll get back into the software when we start talking specifically about the process here. I'm going to pass it over to Armdan, who's going to talk a little bit about VIAS3D's background and the software used today from their end.
Yeah, hi. Thanks, Blake. This is Arindam here. So let me go quickly through who we are at VIAS3D. So we have multiple industry experience. So what we do is we get also involved in the software sales and support, consulting and training. But we have people from as many industries as you can think about. So what we have is people who have experience with the nuances of that industry, specific applications, codes and regulations, standards, practices, best practices of the industry. And we have experts who have generic skill sets in using simulation, using the physics-based or multi-physics simulation and various softwares that are available to use them properly. So our team has around more than 70 plus members. It comprises of technical and non-technical team and management team. So we have a strong group of people with PhDs and masters who are mostly getting involved in the consulting services and all. With their degrees varies from specific areas of design, manufacturing, solid or structural mechanics, fatigue and fracture, composite, optimization, reliability, data analytics and system and hardware architectures. As I mentioned before, so apart from engineering consulting services, we also provide product lifecycle management, whether it's consulting. We do a lot of training, whether it's off-the-shelf standard training or we do a lot of customized trainings. And of course, it comes without saying that we also help with automation and customization. And I think today's presentation is sort of a look towards our customization part of it and also how we collaborate with other solutions and other companies to provide the best value for our customers. We are also a value-added reseller of the source system. We are their platinum partner. That means we are one of the resellers who are doing the job right in terms of client satisfaction and all. We deal with on Simulia side because we are talking more about structural simulation and all today. So on Simulia side, we work with softwares like Abaqus, iSight, Fesafe, and Tosca, and some of the softwares we have used in our workflow today, which we will demonstrate in our the slides coming forward. We also work with CATIA, which is a design software, Delmia, which is a process manufacturing automation software, and Enovia, which is a collaborative environment. Going to the next one. These are kind of overall view of what we do using finite element, computational fluid dynamics, and electromagnetic simulation for any computer-aided engineering applications in various industries. So it's we work with different material modeling, different nonlinearities, be in terms of contact or large deformation. Also, we work with implementing a lot of standards and codes applications. We write customized and client-specific needs. We build those solutions within the general software environment. And for consulting services, we of course provide the client with the direction and help them with their design through virtual testing and all. So there are more details to it, but for brevity, I just want to present one slide sort of showing that if whatever industry you are in, we'll probably be able to help you with our solutions. To the next slide, please. Yeah. Now, so majority, there will be two parts in this webinar, which is the nTopology part that Blake talked about. Now, doing the finite element analysis, we have used abaqus for simulation capability, especially in the nonlinear domain and all. So there are different aspects of a realistic simulation. We call it realistic because in nature, what really is happening, we kind of break down into different physics, and if we can capture the physics properly in the software and also the required input data, of course, there has to be, the data has to make sense. But if you do not have the exact data, then there are ways to look at the variability of data, which also we oftentimes have to deal with. So these are the main aspects of any sort of abaqus structural simulation. I would say structural or non-structural, it can be fluid and others. So, but this example is more using for structural. So nonlinear material property, any sort of nonlinear analysis. So material models in abaqus, there are standard material models, but then you can also write like wrapper codes around the kernel of the software, where we can bring in new material models, and then it interacts with the general framework of the software. So nonlinearity can come from large deformation, contacts, fatigue and fracture, which is kind of a singularity problem. Like either you will have a surface being split into two halves and all this. So those are very well captured using abaqus. We perform a lot of design optimization, reliability studies. And of course, it can interact with other software, and also within abaqus, there are some multi-physics capability available. So you can do thermal structural or thermal fluid kind of simulation or soil structure interaction. And this is kind of showing that with adding all this complexity, end of the day, we will have a high confidence. Of course, your model has to be verified and validated. But once it is done, and typically we go with validation with proper test data, then we'll have the confidence that the model adequately represents for the purpose, for the interest of that problem, what is happening in an actual scenario or in a natural scenario. So we can perform a lot of virtual testing, and that's where you start seeing the value that this software or this approach adds up to. Going to the next one. This is overall Simulia portfolio, so I just want to take a moment to describe. So previously, what I talked is kind of the finite element part of it, which is dealt through abaqus, but there are other software solutions within that Simulia portfolio, and abaqus is part of it. There is Tosca, so Tosca has structural and fluid optimization capability. On structural, it can do shape optimization, topology optimization, and all. Fesafe is for fatigue analysis. So there is a critical plane method and all this. I have one slide dedicated on Fesafe. We'll talk a little bit more there. So it does the fatigue life calculation. It takes the stress or strain values from an abaqus or any other software where you can run the FEA, and using those stress strain values in the model, it does the fatigue assessment, fatigue damage assessment or fatigue life assessment. There are material properties also inbuilt in Fesafe, which is more on the metallic side. So if you have a rubber-like material, then the mechanism with which the fatigue is driven in a rubber-like material is different than metallic material. So there is another software solution which is available for that comes as an add-on with the Fesafe. Eyesight is for today's presentation, we are using a different solution for that, but through Eyesight, it's a workflow automation component, and we can also do optimization, design of experiment, reliability studies, and all. And apart from doing the workflow automation and having those those optimization and reliability capabilities of formulations, it also can transform your any sort of explicit modeling like finite element and all to a response surface. And once you get the response surface function, then it becomes more like solving algebraic equation, which is very fast, and you still there are some checks and balances, of course, we have to do. And then you'll be able to, it's like almost a representative of your FEA model. So you change the parameter and still get the output of interest with fidelity using an algebraic equation. Then if you're working with a Monte Carlo sort of simulation or optimization where you need to run many samples, then the efficiency increases. Yeah, going to the next one. So this is a little bit on granularity of the Tosca. So in Tosca, you can do topology and sizing optimization. So typically in topology application, it will be finding the design. You will start with the initial design, or you can include the entire design space, or it can be some initial thought process in your design. And then it will try to, with the proper algorithm, it will try to find the design that will maximize the stiffness or minimize the weight. So those kind of scenarios. And there are various algorithms available. So based on application, you might have to use one algorithm compared to the other. And then there is Tosca structural sizing. So it reduces the mass through the optimized sheet metal thickness. And this is a very typical automotive application. But you can, even in consumer product goods and all, we are kind of using the similar workflow there. So these are basic. I mean, it doesn't really relate to a particular industry, but application may be more common in one industry. But that's where our multi-industry experience also work out. We always want to help our customers with experiences from a different industry, because kind of fundamentally the problems can be very similar. So that's where we try to always address. Also, we can do a shape optimization, so it reduces local stresses, and it can be any output of interest. It's one of the major applications for durability, and in today's analysis, we have used the shape optimizer for minimizing the local stress and increase the fatigue life. But it can be for any output of interest. So as you define your objective function, it will minimize or maximize that objective function. For Tosca structure, and another one is the bead optimization. So this is more of a CPG kind of example. You can think of the bottles and all. So it increases the stiffness or the eigenfrequency for either sheet metal structure or any sort of like, something which has a very small, very minimal thickness. So it doesn't have to be a metallic structure. And then in addition to that, so Tosca can also be used for, it's the Tosca fluid part of it for topology optimization. So we can look into the channel flow to reduce the pressure drop and all this. So again, you define certain flow criteria, and then it works with the geometry, and then how the geometry imports changes on the fluid parameters, and then optimizes for the application of interest, which most of the time can be pressure. Going to the next one. Now we are talking about Fesafe. So it's it used to be an independent standalone software to solving mostly metal fatigue. So it has been included in the Simulia portfolio. It was developed in 1990, and since around 2000, it started close partnership with abaqus, and now it is fully. At the time, it was abaqus, then it became Simulia, and now it is fully integrated with that. What it does is, and many places we actually use more Excel spreadsheet kind of analysis, but it does, I mean, there are a lot of complexity in a fatigue analysis. Just getting the stresses and strain is not enough. You have to look at different planes, especially if there is a multi-axial loading and all this complexity is there. There can be also plasticity, plastic response, which kind of changes. There is a correction to your fatigue life and all. So Fesafe brings in all this within your entire model. So, and it can check for every nodal point and all. So you have tighter control on the domain for your fatigue analysis, and also you can introduce a lot of realistic complexity that actually plays out a significant role in fatigue analysis. So you are doing less sort of assumption and using the more accurate physics, because fatigue life typically has a lot of variability even in the material properties. So it's better to always capture as much physics as you possibly can. Going to the next one. Yeah, and this is, we'll talk more about that. So 3D Experience is a product lifecycle management platform. So it's not just like a software package, and then it has multiple softwares and all included, CAD and everything, and it works seamlessly together. And one of the things we are going to show you is the process composure, which is, you can think of Simulia has eyesight, so it's more similar to eyesight on 3D Experience. So it's a role based because you can also, like, when you are developing something, so one of the main problem is who is doing what, and also having silos in individual areas in a company. So it breaks all the silos, and it also helps with having individuals as roles, so that there is a lot tighter control on the process. So there are a lot of details to it. It probably will take many webinars and all. So we just wanted to touch base. If you guys have more questions, we'll be more than happy to answer or get to a meeting with you all at a later time. So that's kind of an overview of 3D Experience platform. Yeah. Going to the next one. Yeah, so now I will hand it over to Blake. So we'll talk about the problem statement, the objective of this, and then we'll go from there. Thank you.
Yes, thank you. So now that we have a background on kind of all the software used, let's talk about what we're trying to do in this example to demonstrate all of these working together. So we're looking at a connecting rod here, and our design goal is to fill this center section of the lattice with a, fill this center section of the connecting rod with a lattice that supports the loading conditions of the force here applied at the top in the Y direction, while the bolt holes here are fixed on the bottom. And we're not just starting with this, we also have a field of actually a topology optimization result, but this could be anything. This could be experimental data, it could be simulation data, but we have some idea of where a structure like this would be, where the stress would kind of flow through it, right? And so this is, in the animation, I touched on this earlier, the color is kind of demonstrating in 3D where you'd want to have more material in the red and less in the blue. So to reiterate our design goal, we want to find that lattice that minimizes weight while ensuring that the max stress in this doesn't exceed some kind of value. So we want to find that balance between the stress response and the weight by choosing a lattice. And beyond that, we want to check for the fatigue life. And once that optimum kind of lattice design is found, we want to perform fatigue life analysis and modify the geometry where we might see fatigue life issues. And that's done with Tosca and Fesafe. So with lattices, you do have a lot of potential stress concentration. So we're doing that to mitigate that effect. And I want to reiterate, this is just a small example of thousands of possibilities where all of this software can be combined. You don't have to be looking at a lattice. You don't have to be looking at a connecting rod. We're just talking here about setting up some kind of design variables and some goals and trying to achieve that by connecting various pieces of software. So the design variables we are looking at today, we're looking at the lattice type. So how are we going to lay out these beams within this lattice? We are looking at beam-based lattices only for now. The scale of the lattice, so what are the size of the unit cell for that? And the minimum and maximum beam thickness. So like I said, that is going to be tied to this field here. And where we know we want to have more material, we set that to the max lattice thickness. And then where we know we don't need as much, we set the minimum lattice thickness. And everywhere in between, we're interpolating between those two linearly. So that's where I say lattice beam thickness is scaled linearly from a min to a max value depending on this field, this topology optimization field. If we go to the next slide, we'll talk specifically about how all of this is done, step by step. And these are kind of labeled by the software that's being used. So you, as an engineer, would start here defining some material properties, a CAD geometry, and some loading conditions. In this case, we just have one load case, but we could have multiple. And by the way, it's the material, it was on the previous slide, but we're using titanium Ti64 in this example, easily changed out to anything else, but that's what we're using today. So these three things are kind of how you start any kind of engineering problem, right? And we feed that into first a kind of pre-processed topology optimization on the bulk CAD geometry. So on this geometry, we perform based on the loading conditions and material properties, some kind of analysis that gives us a field of kind of a starting suggestion of where we want to have material and don't want to have material. So that animation I've shown several times, we're getting that from this topology optimization kind of pre-process. And this is not in the loop that's getting cycled through. This is just to give us an idea of where we want the lattice to be thick and where we want it to be thin. And like I said, this doesn't have to be from this step. It could be from experimental data. It could be from another kind of analysis. But the lattice infill, the first step we have here, is driven by the data from that. So we have some kind of field we're using to drive the lattice parameters, right? And so that's that pre-processing, and you'll see the CAD geometry also goes down into this nTop file, which has the beginning of our geometry creation in earnest. So we have the field data coming in, the lattice thickness based on the top op result, and we have the CAD geometry, and that performs in nTopology a lattice infill, like I mentioned. And the key inputs that we've selected for design variables are isolated in the nTop file, you'll see in a second, so that we can easily change them and the model updates. So after the geometry is created, in nTopology, we're able to mesh it and define the loading conditions and export that as an abaqus.inp file. So that's all set. The material properties, the mesh, the loading conditions are all packaged up and in a format that can just be sent to Abaqus. You press go on the Abaqus file. Obviously, it's done automated. through Process Composer, but that's all very convenient. So you'll see this arrow up here is showing that the loading conditions are coming in and going into the model export as well. So the CAD geometry and the mesh and the kind of analysis properties like material properties and loading conditions. And here you can see an example mesh. So from there, we go to the structural analysis performed in abaqus. And this is where our loop starts. So not shown here, we're also getting the mass of the part from Antopology. So we're able to weigh the structural performance, right? So the stress response of the particular design and its mass. And we cycle through X number of design variations. In this case, we did 50, but we're changing these lattice parameters, sending it back here, and repeating this until we have a wide sample set based on a variety of lattice options. And as this process is repeated, once it's all samples are analyzed, we find a design, an optimized design, right? So we're balancing weight and stress. And with a lattice, it can be hard to guess what would give you that. So this optimization is very useful. Now, once we have that optimum design, we're not actually quite done because like I said, we want to worry about fatigue analysis. And so that's where this next step comes in. We take our optimum design, but we do a fatigue life optimization based on Fesafe and Tosca. And we'll talk more specifically about what that looks like. But after that's done, we have our final design. So it's been modified by this final fatigue life optimization. So not only do we have a lightweight part, a good stress response, but also no concern about, or let's say a lower concern about fatigue life with a lattice. We can go to the next slide, please. So just to zoom in a bit on nTopology, I wanted to show kind of what the steps are to the nTopology part of this. So this is, you can think of this as just a zoomed in section on what we saw in the beginning cycles of the loop. So you see there's an in and an out here, right? So that's what's coming in and out of nTopology through the Process Composer. So you have that CAD geometry. It's going into an automated process that separates the outside frame geometry and the lattice infill. And from there, we generate a lattice at the lattice infill volume. So the center solid region is filled in with a lattice. And going into that, we have our field to control the lattice parameter going into that lattice generation, as well as our lattice parameters. And this is the first time I'm showing what the lattice parameters we're manipulating are, but I'll go into further detail in the next slide. But what we're dealing with here are the lattice scale. I guess I have mentioned the lattice scale, the thickness, and the lattice type. So we'll see those in detail in just a second. But yeah, you can see those are what are being manipulated by Process Composer so that we are generating a new lattice every time we run nTopology through this. So the lattice geometry and the frame, you see the arrow coming down from these two channels are getting rejoined into a final geometry. And we can apply a blend radius to make sure that that blends very nicely. And we trim the body up, trim the lattice up, and mesh it for a finite element mesh. This can be done really quickly with our meshing software. We're not getting into that today, but very robust and fast meshing algorithms through voxelization. And from there, the two things we're outputting from that nTop is the abaqus model file, right? The thing that's going straight into abaqus, and also the part mass. So those are joining in and going out. And like I mentioned, the loading conditions and the material properties coming from the beginning of our kind of selection process, those are collected into the abaqus model file through nTopology. So again, the key inputs, lattice properties, the key outputs are something that's ready to go to abaqus and the part mass, so that we can get a stress result and weigh that against the part mass. We can go to the next slide. So I just want to show really quickly the design parameters we're looking at. So the first we're looking at are a sub-selection of lattice types. We actually have, dozens or, even more than that lattices you could potentially make, as well as custom lattices and non-beam based. But we're just looking at a subset here of popular lattices: body-centered cubic, face-centered cubic, diamond, octet, Kelvin cell. And so you see they range between those, and also different minimum lattice thicknesses. So that's where that optimization field is blue, or less hot, and as well as what the lattice will be at the more important sections of the geometry where the optimization field is red. So we're controlling two parameters of the lattice thickness. So that makes optimization really important, because it can be kind of hard to intuit what the proper values of two different lattice thicknesses should be. But with this, we're utilizing that field while being sure we find an optimum solution. And then lastly, we have the lattice scale in Z. So you notice we're just actually scaling the lattice unit scale in the direction that goes up the connecting rod height. So you see they're just getting stretched. So the XY unit cell size does not change. So we always kind of have this clean bridging of the lattice across the walls of the connecting rod. But we are looking at the lattice scale in Z, and that's just more of that's not by necessity, right? We could look at more properties. We could look at a uniform lattice scale size, but that's just something we did. And you can see just a little snapshot of nTop here, how quickly we can update these parameters with the GUI, with the graphical user interface, and see the resulting body change. So I'm just looking at different lattice types, Z scales, and thicknesses. This is actually done through a headless command line interface, right? We're just controlling these inputs with a file. But here you could just see how the nTop file is set up, right? You have some inputs here, like I specified to the left, and you have an output, like the final part, or the mesh and the abaqus model, things like that can all be outputs. So like I said, we're doing 50 design variations of here. Glenn will talk more about that in just a second. But those are the range of design parameters. So keep in mind, it's not just this 20 designs, right? It's a combination of these parameters all being cycled through and sampled. So you might have, this Kelvin's, a Kelvin cell with a certain max min thickness and Z scale. If we can go to the next slide now, I think this is where I can pass it over to Glenn. Now that the Antopology side is kind of laid out, hopefully very clearly, and we'll talk about how that all fits into the rest of the software we talked about.
Thank you, Blake, and thank the whole Antopology team for doing such a great job, and not only that, making this whole process intuitive. The ability to change parameters quickly, and you'll see, how quickly when we run this process made doing this really intuitive. So we're looking here at the workflow as it stands. We've got a workflow, and then we've got a DOE at the top. So we first download some files, and I'll go through that. Then we go ahead and we create a file using the text parser. And that file created is to control the parameters for nTopology. And then we run nTopology in a command prompt. And then the second text parser is to collect that mass data that we talked about. So each iteration it runs collects the mass data. And then we run it through abaqus and then upload the results to the platform. So talking about the Process Composer is a 3D experience application. And no longer are we tied to using the software that's in our portfolio because Process Composer can connect just about anything. You can use the best software for the job, as we did in this case. So, now you can, run in one thing and check in another, and the parameters are all accessible. So we'll talk a little bit about the design experiment here and what we did to explore the variations of the design parameters and identify the best design that satisfies our requirements. In this case, our requirements were a weight requirement and, of course, a stiffness requirement. So the parameters to consider was the strongest design and the lightest weight. So we were to investigate the relationship between the design parameters and their influence on the performance objects to improve the design. So, you know, in doing this, we look at this very quickly and, you know, get comprehensive insight into what works and what doesn't. So we have a multitude of different shapes for our lattice, and we have different thicknesses and different heights, all placed in strategic places. And we can look at those very quickly to identify which ones work and which ones don't. So I'll do a really quick video here that steps us through the process of how this was created. And let's see, let's just run. Okay, so let's take a look at the workflow. Again, I explained this before, the different things that it goes through. And the very first thing that we have to do is we have to connect all of the files that we want to run in this process. We're not uploading them all, we're just connecting them. So we're basically telling Process Composer what files we're going to be getting. We have specifications, internal data, and results. So the data that we are going to upload or download into a runtime folder to run Process Composer and Abaqus are brought up. And then we use the text parser again, which I'll show in a minute, a little closer. And then, of course, we run the command line for nTopology. And you can see there's an input and an output file. That's what controls the parameters. And so we're going to use the text parser again one more time. And if you can look here, you can see all the parameters that we can create, read, and write. And then we bring it into Abaqus to run. So nTopology creates the scenario completely and the FEA model. So all we have to do is run this from a command. So, and it does it very quickly. You can see when we do the design experiment that we do, in the video we did 40, but we did 50 for the actual project. And then we upload the results to the platform using an uploader. Once you get that to run, that's when we create the design experiment. And now the design experiment can use all the parameters that we've already created. But in here, we have different ways we can run experiments. We can automate and use different types of Latin hypercube or so, you know, anything we might want to use. But here we're going to use a data file because we wanted to control what we wanted to see. So we were going to pick the lattice type, the Z height, and the max and min thickness. And here, each lattice type has a variable number of different designs that we ran an experiment on. There was 40 in the video. And again, we did 50 for the actual experiment because we thought we could expand it. And you can see all the different, you could do 100 experiments. It would be simple enough to do. It just take a little bit longer to run. We're going to run it. And I actually cut the runtime out of here, but I will tell you it was 20 minutes to run these on the computer. So that's just to say that nTopology created all of those in that amount of time. So it's very quick to mesh and do everything else. So here you can see what ran and what didn't. If you had a failure, it would show here. And then we have, you know, all of the files where they're ran and where they're not. And then we go ahead and we take, to see the results, we can go over to our results in analytics. And this is really easy to use. It's click and drag. So we can actually just drag this in. And I'm just showing you we can drag it in. I already have it created there. But you would drop it in here to create it. Or you can rerun one that's been run already by just dragging it over and dropping it in. So we already have it in there. So I'm just going to click run. And we run the case. And this is not time cut out. This is actually the runtime to create the result. So basically, we can see all the inputs, and we can see everything that's run. But now we kind of want to define the experiment a little bit, or not the experiment, but the results that we want to see. We look at the priority level over on the left, and you can have a min and max threshold. And what your objective is to do, you want to minimize weight. And all of those things go in an order. And then you can look at the parameters that we're going to use. And this is these are the results here. So it's really quick and easy to just look at these and just, see at the blink of an eye what's good, what's bad. You're ranked based on what you chose on your rankings. And so you may not want to see all of these because, again, 50 results, that's a lot of results. So let's just say that you're going to pick 4 or 5. So basically you add those to the cart to compare, because you probably don't want to compare them all. You can see right away what's not going to work. Doesn't meet your criteria. Or what is the best. You have different ways to view these charts, and you can pull the slide to look through the experiments and see. We can also look at the plots. All of this can be easily put into a report and really clear up for anybody that's asking, what worked and what didn't and what direction to go into. So we've added 7 to the cart. So we've got 7 up there. And you can look at what we predicted, what are predicting. And then compare the results. They give you a quick snapshot of what these things look like right off from what to use. And that's all done in one run. So, Process Composer is just a great way to look at these things and to save a whole lot of time with your design and where it's going to go to. And at this, we're not done with this. We're now going to go into doing a further analysis, and I'm going to hand it back over to Arindam at this time to talk about the fatigue life.
Yeah, hi. Thank you, Glenn. This is Arindam back here. So I think we are running a little bit tight on the time, so I would like to go through it as quickly as possible. So what we have done here is, with all this initial optimization and all, the idea is to look at more at a smaller scale, sort of. So you look at the local distortions and how the stresses are, and because fatigue is a very localized phenomena, so there is always a concern that although you are structurally very sound in terms of your stress strain compared to your yield, but maybe there are fatigue concerns in small spots where it can initiate a crack. So we use the Fesafe. So Fesafe uses the solution from abaqus. So we apply the force, the loading on the structure, get the stress strain, and then use those in the Fesafe. And then Fesafe goes through, there is a critical plane method, which it looks at all the resolution of all the stress tensors in many different planes, not only just the plane of the max principle. And then based on at each nodal point, then it will calculate the damage, and then with having the damage values from all the nodal points, it will choose which one is the worst scenario and report that as the fatigue life of the structure, because all it matters to initiate one single crack, and that can fail the structure. So based on that philosophy, Fesafe gives you this output of the fatigue life. Going to the next one. Can you go to the next one? Yeah. So now once we know how to calculate the fatigue life, then what is the next step? The next step is actually to do something about it. Of course, this numbers, I won't put too much attention on the specific numbers. This is a sort of a made up problem. So we wanted to emphasize the effect of using this approach. So some of the numbers are a little bit scaled up. We generated the problem in a way that this thing shows up. I mean, you may not have that much or shorter of a fatigue life and all, but it's the improvement that we should talk about. So what we are doing is, now that we know the fatigue life, so all we have to do is run an optimization algorithm and then keep changing the design, and then output of interest comes from Fesafe. Then Tosca looks at that output of interest and sort of like a marching algorithm. These are marching algorithms, so it goes to a next design iteration and all, and efficiently comes to a solution where, given all the possibilities of changing the shape, it will come up with a shape that will minimize the fatigue damage or increase the life. So that is what it is showing up here. You start with the initial number of cycles, say 75,000 or around, but then it increases the life against fatigue to almost like 112,000 cycles. And you can also see the change in the shape. So it's kind of making it more like putting more like a fillet. Again, this is an example. It can be very complicated shape and very unintuitive shape that your optimization software will come with. And that's what the beauty of all this mathematics-based software solutions are. Going to the next one. I think, yeah, this is just showing some of the numbers. So stresses have been reduced. Again, 24 MPa or 20 MPa or 40 MPa, that's not the main point, but you can have a reduction in the stress. And if it is a strain-based problem, then of course, I mean, we have showed here is a stress-based problem. It can be a strain-based problem as well. Fatigue life have been increased, is increased by more than 50%. Always remember, this number may seem high, but there is a lot of uncertainty in the input values of any fatigue calculation. So there are high factor of safety that every industry application puts on a fatigue life. So this although seem quite a bit, but for fatigue, you want to be safe than sorry. And then it also tells you what is your optimized final structure. Then you implement that design, and that is something you can either print with an additive manufacturing process or traditional manufacturing process. Yeah, I think that kind of concludes my part. So the next one is, yeah, like if you
I'll just jump through the conclusions very quickly because hopefully that was very clear. But we've created this automation process to do a design experiment or a design variation analysis, and given us a good lattice selection based on scale and thickness and type, and then did a further optimization for kind of the durability and shape optimization based on fatigue life. And this just gives us improvements in design through multiple levels of optimization and sharing the process among a lot of advanced software. So we have some next steps here. We could look at different kinds of lattices. This is an example of a gyroidal lattice. We could look at more multiple loading cases simultaneously. Maybe consider manufacturing constraints, outside of either an additive manufacturing or inside of that. And if we go to the next slide, I'll just thank everybody and try to jump to the questions very quickly. So I have some questions here. First, is the geometry modified in Tosca or in nTop? So the final geometry modification around the fatigue life, that was done in Tosca. It does not have to be sent back to nTop. It's performed on the mesh. But there is certainly a geometry generation occurring, with all of these design variables you see on the screen in Antopology. The other question is it possible to do point impact on a circular design in Antopology? So there is simulation techniques within nTop, but they're going to be limited to linear static analysis. So if you need kind of deformation or non-linear analysis or transient, you'd want to, in this case, we can just export a model out to another simulation software. So you can look into that if nTop's native software, native analysis tools aren't able to capture the physics you're trying to do. And then is it possible to get the function in nTop? I'm not sure what this last question is. It says regarding lattice type, how is it possible to get the function in nTop? I suppose you mean how does it generate the unit cells? So we have a selection of different volume lattices that are beam and face based. We also have other types of lattices. You can search our support site, support.antopology.com, for other kinds of lattices. And we also can generate custom lattices and populate volumes with those through whatever geometry you can either bring in as a mesh or generate in nTop or CAD.
Thank you, Blake. And I'll take the next couple of questions. Okay, and the first question is, can Process Composer be used with other software? And the answer is yes. You can use it with almost any software you can run a command line from. The next question is, are the tokens used on your machine or on the cloud? And the answer is you can use either the ones on your machine or on the cloud. The next question is, when you're running design experiments, are you actually creating the models? And the answer is yes, they get created and run in the runtime folders, and then they get deleted. You can, however, not delete them if you choose to and build them up. Okay, can multiple experiments be run? And the answer is yes, they can be. You can run multiples in a loop, subflows, anything you can think of. Then the next question I see is it possible to incorporate the same workflow in iSight? And I would say yes, you can. The difference is Process Composer is connected to the platform, which will allow you to run all of the platform apps. Okay. What we do, one of the things that we can do for our clients as well is regarding software sales, support, and training and consulting. We can offer customers is we can provide software solutions for the entire DS portfolio, such as Simulia, CATIA, Delmia, or Novia. In addition, we have a strong technical team that can provide technical support, either implementation or installation of products and related questions. We can train you on those products either at your facility or ours. We can also arrange online training if needed. As a part of the technical services and software solutions, our resources are not only product knowledge, but provide a technical service in multiple industries such as gas, life sciences, aerospace, and automotive. And I want to thank you and then hand it back over.
Yeah, I think that'd be good since we're up at the hour. If there's any questions, go ahead and contact us we can do marketing at nTopology.com, and I'll make sure that gets fielded to the engineering team for answering those questions. And I think that's it. We will send everyone the recording afterwards.
Thank you all.
Okay, yeah, thank you very much.